is this disturbed rock zone really confirms the mechanics of what's going on. The imaging of the 3D seismic confirms that the rock is breaking up in this part and flowing into the cavern through the mechanics of what's the rock mechanics. So what I'm going to move on to here is these burbs. And you've seen this, the internet sensation of John Boudreau's videos that are posted online. And we think we've got a pretty good handle on what's going on in those burbs, and I wanted to kind of explain that a little bit more to you today. So this is the event that happened on the 21st, August the 21st. It's the one that was on YouTube and all that. This was kind of the situation before. So what we have is we have the sinkhole, and beneath the sinkhole we have this mud that's forming part of the disturbed rock zone that goes down to the cavern, and we also have trees that are lodged in that material as well. Coming up is gas. And this gas produces this very low period events that you might have seen on the helicorders, the seismic instruments that are out there. As it flows up, this gas actually causes a triggering of slope instability on the side of the sinkhole. And this is a very natural phenomenon. It happens in road cuttings and in open pit mines and that kind of thing. Wherever you have a slope that is slightly higher angle than it should be to achieve stability, what happens is that slope works to obtain this angle of repose, this natural angle of repose. And it's a bit like if you get a pile of sand delivered for some work you're doing on your house. That pile of sand will actually achieve a conical kind of shape, and that angle is defined by the material. Right now, what we have is this very loose kind of mud in the sides of this sinkhole that is quite weak and is causing sliding. So as this gas comes up, it triggers this sliding. This is what's shown on the other side of this diagram. In this particular event, what we saw was actually 3 slides that were very close to one another. This is the pressure recording from within the cavern. So that material that's sliding into the sinkhole is connecting via pressure through to the actual cavern, and we're recording that on the pressure instrumentation on that well Oxy3A. So you get these 3 responses as you get 3 slides. So we had one slide that went in, and then a second slide and a third slide. And what this does is it adds weight onto the disturbed rock zone that is then connected through to the cavern. So you get this pressure response. And of course the trees come up to the surface, and we think that's just actually trees that have sunk and their root balls have been dislodged. So they actually are much more buoyant and float up to the surface. So this is an illustration of this angle of repose. So, as I say, this steep angle, depending on the material, can be quite unstable. And that's what we've seen around the sinkhole. We think that the sinkhole margins are actually critically unstable and can slide at any moment given a sufficient trigger. And what they're doing is they're working to get a much lower angle of repose to create stability. So this sliding or slope failure is very well known, as I say, and that's what's happening. This mud is sliding into the material, is sliding into the sinkhole, and you see the trees going down with it. In fact, if you watch the video very carefully, which is what we've done, you'll see this, the trees just don't sink down vertically, they actually sink down and go out at the same time. And that's exactly this effect. This is the surveying that's being done across the sinkhole. This is a depth profile. Shows a measurement of the sinkhole down to about 160 feet. And what this is showing you is this angle of repose. As I mentioned before, what we were thinking at the beginning was this would be about 25 degrees. And it is, within the sinkhole inner part, if you like. But the outer banks, because of the weak surface material, are taking on a much lower angle of repose, which means the sinkhole is broadening out. So it's down to 15 degrees in places and down to 7.5 degrees in other places. And this is something that we'll be watching through time because we want to understand what this angle of repose is going to eventually turn out to be. Now let's go down to the cavern. And I think one thing that was difficult to explain in July was what's actually happening inside the cavern. And we think we've got a good handle on this now. There's some details that we're still discussing, but we think we've got a pretty good handle on what's happening. This is not to scale, so this is just an illustration of the pipe work, basically, that's going on in the subsurface. This is the cavern. This is the disturbed rock zone, illustration of the disturbed rock zone up to the surface. This is the sinkhole. And we're monitoring the width and the volume of the sinkhole with time. And as I explained in the last slide, the material that's going into the sinkhole is adding onto this disturbed rock zone that's putting pressure down into the cavern. And this is then really a plug that's slowly moving into the cavern. And we think eventually, right now, the cavern will fill with material completely to the surface, to its top. And at that point, the cavern will become stable. Now, above this, this plug is a very loose consolidating mud. You can actually think of this as very gradational. The whole thing, it's like taking a jam jar full of mud that you get out of your backyard and mixing it with water and shaking it up. You can watch how that mud settles slowly with big bits at the bottom and then very gradational up towards the top. And that's really what's going on in the cavern. So over time, this whole material in the cavern will slowly consolidate and solidify towards the bottom. At the same time, more materials coming in and pushing it back up towards the top. So the whole thing will fill. And where we see this effect is in this, these tag measurements that have been routinely taken in the Oxy 3A well. What's been done here is that a metal weight has been put on the end of a wire line and run down 3A well, 3,500 feet into the cavern. And that tag goes into the material that's within the cavern. What it first sees is this very loose, sloppy mud at the top. And eventually it hits something that's much more solid. And something we were scratching our heads over a lot before we kind of came to this understanding is why that tag, the maximum depth that it reached, varied so much. And it does. It varies from one measurement to the other. And this is just measurement uncertainty because the mud is so loose and sloppy. It's basically just going down, feeling some frictional effects from the material that's going through, and then eventually stopping. But that's a very variable kind of depth, somewhere between 3,900 and about 3,600 feet depth. The top of the material is very consistent. It's almost filling the cavern. But remember what I said, that material has got to consolidate and densify. And this is just an illustration, simple illustration of this tag moving down through that bone, feeling this frictional effect on it until it hits something that's sufficiently hard for it to stop. So as I mentioned, another thing that's happening is Texas Brine are installing a geophone array into the salt dome at depth. I just wanted to take a little step back first to talk about the whole micro-earthquake array that's installed at the site. There's currently 5 near-surface stations that are monitoring the volume near the surface, about down to about 1,500 feet depth. There are also 2 deeper wells. These 5 sensors are installed at 80-foot depth. There's also 2 deeper wells, one at 450-foot depth with 3 sensors in, and one at 1,000-foot depth with another 2 sensors. And all these instruments are focused on the near surface, as I say, about 500-foot depth and above. And what we're seeing here is we're seeing micro-earthquakes that are occurring in and around the top of the salt dome and around the sinkhole, and these very long period events that are associated with gas movement with this array. So what we're also doing is we're installing another array in a deep well that's already been drilled. We're waiting for the equipment to arrive. That's going to go down to about 3,000 foot depth. There's going to be 19 geophones within this array that are at 15 Hertz. These are much higher frequency that record much smaller events. And that's critical because we think there are smaller events going on around the caverns, and we want to monitor those events to see exactly what's going on. There's also going to be 3 4.5 Hertz geophones nearer the surface in this borehole. Approximately the top of the salt is here. The array goes in between Oxy 1, 3 and 2 here, so it monitors this whole volume of the salt dome. We're watching to see if there's any instability that's going on within that salt dome that we need to raise, to think is a problem. Right now we don't think there's any, but we're putting the instruments in to monitor that and look for real. So the last time I spoke to you, which is back in March time now, I gave this slide and I wanted to just give it to you again because I think it's important to understand that we are monitoring and we're learning through this project, through what's going on here. So we now have this capacity to observe the rock disturbance around the caverns and the disturbed rock zone. We can observe progressive build-up of activity leading to a sinkhole burst. That's done regularly. We're able to provide this daily safety level that is a recommendation to John to say whether people can go anywhere near the sinkhole. We can observe progressive damage and disturbance of the rock and combine this with our numerical models to better understand the long-term behaviour. We can use all of this to assess the stability and to formulate emergency response plans and further monitoring if we need. This gets fed into the Blue Ribbon Commission for these great minds to really review and to understand better. The measurements can also provide feedback to our simulations, and we can learn from them and develop those as we go. So as I say, we are monitoring all of this and we're responding to the issues that are arising up. Thank you very much.
Thank you.